Thank you very much, and thanks to the people in the first session. This is proving to be a very interesting afternoon. Here at Carnegie Mellon, we have a very, very large amount of computer science going on in many forms. In fact, when we counted, we have about 500 faculty, students, postdocs, and so forth working on aspects of artificial intelligence. So back in January, a lot of us were talking amongst ourselves about safety in AI, and very much the kind of topics which Eric so nicely highlighted for us. And it is something where the stakes are really high. What I'm going to present now for about a quarter of an hour are some of the consensus opinions among the faculty here when we did look at what we can actually do to make sure we get the benefits of extraordinary technology and have it sort of unambiguously be a good thing rather than come with a bunch of downsides. If we get this right, and I think we've only got 12 or 24 months before the true test is going to happen, if we get this right, we will be able to save millions of lives a year, maybe tens of millions of lives a year, through the use of technology in all the areas of the economy that Eric pointed at. If we get it wrong, we're going to potentially see a sudden freeze on AI research or unwillingness to finance work on autonomous systems, which could put back huge opportunities for the human race. So that's why the stakes are really high at the moment. So when we sat down to figure out what should we be doing about this to tilt the odds in the favor of a happy outcome from all this massively complex technology that we're trying to introduce, there really are two parts to it. There's the people and the engineering. This is policy. We absolutely cannot just deal with this ourselves as computer scientists. We have to involve the rest of society. But at the same time, we're technologists. There's a lot we can do in terms of technology for making sure that we don't have an awful blunder. For example, when poor Eric's Tesla finally does plow into the Pacific Ocean and we lose a great computer scientist on the way. So, I'm going to talk about two things, policy and verification. And we're going to actually begin with policy. And I think self-driving vehicles are the perfect example of this. It's something that we've been working on here for 3 decades now. And we've done all kinds of crazy things along the way. And now if you look at what's happening in places like Carnegie Mellon, who have watched self-driving technology mostly move into the commercial sector, the folks who are still working in this area are now asking even more interesting questions about the corner cases or the really high complexity situations that involve self-driving. And one of them is something that Aaron Stein, the first of the folks, is looking at, and it's not the only thing, but it's a very, very pure example of why we desperately need policy decisions if we're going to be able to have AI making our lives safer, and if that AI is going to be, if you like, accountable. So we're going to look at one of the best cases where autonomy, not this kind of hippie human computers working together in harmony crap, real autonomy matters. If you're half a second from your car having a serious collision, your nervous system doesn't really have much of a chance to do much useful about it. And so the computer, of course, on the other hand, has got at least thousands, probably actually millions of CPU cycles to plan through some of the game trees that Eric showed us as to what's going to happen next. And so Aaron, among other folks, have been actually trying to plan out what you spend that half a second of autonomy doing. Now, everything's going fine. There's all kinds of wonderful bits of computer vision in there, great parts of control theory, great adaptive learning of the dynamics of the vehicles so that you know what's going to happen in response to certain actions. And there's huge engineering challenges, all of that. But there's one line of code which Aaron is stuck on, and it's a very critical one. And it goes like this. Among that game tree, in a very simplified form, and of course it's much more complex than this, one of your choices is, let's do this and risk a 1 in 10 million chance of killing the driver. We're going to swerve, and probably the deer will be unharmed as well. Or, this other thing, 1 in a million chance, we're going to risk 10 times the likelihood of killing the driver, but pretty much that deer is toast, because we're just going to plow right through that sucker. So, 2 options, and how do you actually choose which is the best? You need a hash-defined constant in your code, which says, how many deers is 1 human life worth? And we can laugh about it, but someone actually has to write that down. And of course, the last thing I want is Aaron to be writing that down. Now, as engineers, especially with humans having control of the vehicles, we've been able to kind of fuzz that issue for the last century and say, well, it's kind of up to the personality of the person, how much they value life, how much they understand risk-taking and all those things. And so we're not actually going to try to write this down. But now we have to write it down. And of course, I'm sure, it turns out that there is already controversy raging with animal rights activists quite reasonably saying we need to have some open and transparent discussions about what these things are. Because you could imagine a world where we achieve a lot of the life-saving from autonomous vehicles by actually crushing a lot of animals. That would be probably wrong, but we have to have society as a whole and the values of our society helping us decide that. And basically, we're stuck with implementing these kinds of things until we get that going. There's urgency in this. Now, animals are one thing. The really kind of important issues are, for example, now, this is some work by Marshall Hebert, head of the Robotics Institute, and Chris Catani and a bunch of other computer vision folks. We have the ability to do a fantastic job of tracking everything that's going on at busy intersections, even to the point of having reasonable estimates of the probabilities of various scenarios unfolding over the next 5 seconds. And so you can imagine, and this is what they're working towards, systems which actually tell vehicles to do emergency stops or close down intersections if there's a certain chance that someone's about to get killed. And this would be wonderful if it's implemented correctly. This is not a trade-off thing as to whether to put this technology in place. This can, straightforwardly, make driving around cities as pleasant as they are right now while reducing a lot of deaths, or it could make it even faster to drive around cities while keeping the number of deaths constant, depending on where you decide the parameter. And although it's kind of amusing, it's really, really important that there is some mechanism in place where we can start to make these decisions, because if we don't, they're going to get conflated with this much more mystical question of whether artificial intelligence is in itself inherently an evil thing or a dangerous thing, because there will be tragedies where an autonomous system, which on average saves 100 lives for every life it doesn't manage to save, will make the wrong decision. And when that happens, we need to have a sound legal and insurance footing for this. And I think we computer scientists have been working very hard on this stuff, but it's really our responsibility to make sure that legislatures, and I do think this is a role of government, come in and help us actually have processes in place for making these decisions. As Eric mentioned, in the world of drug trials, we do have some sort of protocols. They're very imperfect, but at least they're there. We also have this in place for civil engineering in general, where when you build a bridge, you actually do account in the budgeting for the bridge as to the cost of a human life that you're expected to save or not save, depending on how you construct the bridge. So we have to do it, because until we've done that, we're in great danger of the first of these autonomous vehicle accidents that we encounter, pushing the industry back 5 years, and potentially through that costing tens of thousands of lives. Now, that's the policy part. The verification part is also extremely important. This is the part which is, at least I feel more comfortable with it, because it's something which is under the control of us technologists. We're not having to ask other people for help. So I want to just give a little overview of some of the main lines of attack. And as Eric, I strongly believe that there are rich new open areas. Students or junior faculty in the audience, you should take up the challenge of some of these topics. They're very rich, likely to result in you getting your work having proper impact. And funding agencies or funders in the audience, you should be helping really prioritize these general areas. So, first example of this is something which Eric alluded to. This is work by Mike Koopman here at Carnegie Mellon, which is just to do with testing. And in software testing and in product testing, the old heuristic of take this thing and run it through 100 tests so we can really check that it's working no longer makes sense. And the reason we've got this huge combinatorial explosion of possible situations to test is when you have an autonomous system which is learning and designed for the open world, you have Googles of possible lives that system could be leading. It could be on a military vehicle which is initially deployed in Alaska, then does some work over in Japan, and then gets put into the desert somewhere, and is going to be learning all the time. And for that life, where it's dealing with really optimizing itself for lighting which has a lot of reflections from snow, where it suddenly finds itself in the desert, will its machine learning systems be smart enough to do the kind of things to adapt when the time comes? Now, this kind of problem, what these guys have really pushed for is turning it into, and this is echoing some of Eric's comments, it's turning into a meta machine learning problem, which means that you actually do run your system in hundreds, maybe thousands, and in some cases even more than that number of test cases, and then in a mechanism which is very, very, very loosely related to the idea of playing a game of mastermind, you specifically work out which are the situations which you think have got the most likelihood of being able to actually tax the system or take it into unknown areas. So they've had great success at doing this, and one of the main use cases for them at the moment is in US Army and US Navy testing systems, where Larry Schutte, for example, in our research, has pointed out several times in the last few years that for weapons platforms and for transport platforms which are designed to save lives, in each case the time to deployment of these systems as they get more complex and more adaptive is suddenly spiraling to years and even decades because it is so hard to test and validate them. Another example, which interestingly, even here at Carnegie Mellon, where we tend to all love each other, it's still intellectually a massive war that's going on, is instead of saying we're going to do stochastic testing with a whole bunch of test cases and then use some sort of statistical inference to get a feel for whether we've tried everything, the opponents of this are the folks who like to do full-scale theorem proving. And Andre Platzer is one example of someone who has really been working on taking Floyd-Hall logic, that very old-fashioned thing that we used to all learn about, and occasionally people built systems for trying to validate software systems, and combine it with geometry and nonlinear control systems for proving various properties of systems. One of the places which he has applied it most recently is in the new collision avoidance system, which the FAA is going to be putting into practice in 2017, just 1 year from now, where just by attempting to prove that the control systems are safe, it was able to come up with very, very many edge cases where it actually wasn't safe, and has led to several iterations of completely redesigning the new system. So I'm very excited about this. Old-fashioned theorem program proving did find its place in software development, even though it is not something that you see in modern SDKs. It's possible that the geometric aspects are going to actually be more relevant for AI-based systems, especially ones with adaptive control. Now here's a topic which I'm very passionate about, and just so you know, I was in industry for almost a decade before I returned to Carnegie Mellon. And in the industry work, I was responsible for some large machine learning systems for a big search engine. And one of the things that struck me, and it still amazes me since I've returned, and I'd be delighted to discuss this afterwards with people from industry and from academia and government, is an extremely different approach to testing adaptive systems. In the search engine company, we had probably more than half, maybe up to about 60 to 70% of all our work on our big machine learning systems went into testing them. And by that I mean the way the machine learning system is designed is quite carefully engineered so that as you discovered something that you think is a better model, better learning algorithm, different structure for your learning algorithm, different loss function, maybe different ways of optimizing the parameters. It is then quite a hairy protocol, very similar to the big pharmaceutical protocols for getting that launched to the point where it's affecting 1 billion people a day in what information they're getting. And this protocol, we and many other folks in industry have been designing it from the seats of our pants to do things like here's one unwritten rule. If you're going to launch model n+1, you make sure that model n is still running on a fraction of your traffic or a fraction of your vehicles, so that when model n+1 seems to do something strange, you can start to diagnose whether the strangeness is due to the environment changing or due to something that you haven't thought about in your new model. It's a pragmatic rule of thumb. It doesn't feel super scientific, and this is true of much software testing, but that is just one component of all the things that you do as you're launching new machine learning models. There's so many ways that something you launched in the summer can start to get confused as fall comes in, or as a major European country decides to leave the European Union, or major events like this. You are going to see suddenly a rise in errors in various subpopulations of your queries, and you need to quickly be able to diagnose what's happening, especially when you're using incredibly advanced machine learning algorithms which weren't around a year ago, so you're not quite sure whether they really work. Now, in the area of large search engines, they're usually not directly lives on the line. In something like transportation or medicine, of course there is, and there are opportunities for us to deploy machine learning systems which are learning from trillions of events per day in each of those areas, but we want those systems to work successfully while they're going. Let me briefly mention some of these other bullet points here, because they're all really interesting. Bullet point number 2. Someone comes and tells me, I've got a new machine learning algorithm which is going to predict, say, spam in email twice as effectively as it's been predicted before. We really are going to want to test that out. And you're going to want to test it out by running under all kinds of hypothetical scenarios. You're going to want to ask a question like, is this gender biased? Make sure you run the full system, every aspect of the full system, while withholding any information which we believe could be correlated with gender, to see how it's going to perform then. And hundreds of other questions like that. What it means is to launch a big system which we're expecting to maybe use thousands, maybe millions of compute nodes to do the machine learning. You've got to run hundreds, maybe thousands of similar sized training systems in the development of that system. So you cannot afford to say, I'm going to invest all my compute power just in my live production model, because you have so much what-if testing that you need to do. And Eric has already uncovered the very interesting world of adversarial machine learning. There are already, and I've seen all of these, specific sub-disciplines of how you can be adversarial. One of the really nice one is the ramp-up attacks, where you know that the machine learning system is going to spot your evilness sometime, so you very quickly try to invent a generator for millions of different instances of that evilness and have them all run for 5 minutes each. Before the system can adapt to it, you've already switched into doing another one. Another really worthwhile thing to do is to actually start your operations at a point like in a major flood or a storm where all your deltas are going to be very large anyway, so any kind of scan statistics you're running on your overall marginals is completely confused as it is. So, okay. So I'm going to finish up here. I do think that we are in a very interesting and important point for artificial intelligence. We, the community of us who are building it, building the machine learning underneath it, building the optimization algorithms behind it, we're very lucky that we have the opportunity to make the world a much better and safer place for its population. But we could screw it up badly. And I think there's 4 groups of people who need to take action at the moment. First one is policymakers. I can't just complain that they're not working. I don't think we engineers have done anywhere near enough of a job of reaching out to let them know how important what they're doing is, what they need to do is, and they've got to help us fill in those hash-defined constants. If you're running a company which is fielding any adaptive technology at the moment, my personal belief is that you are completely irresponsible if you unleash unvalidated artificial intelligence just to see what happens. My advice to a CEO or a head of engineering in any of those companies is if someone tells you that they've built an adaptive system, first question is, I need to see the test plan and the test protocol. And it cannot be the same as the test protocols that you've used for previous products. We scientists we got to protect each other's ability to do good work by not running experiments which are going to potentially cause a disaster which will create another AI winter. And in the world of startups or services companies, or even for the Microsofts and large IBM, or companies like IBM, whose part of their business is B2B work, there's going to be a huge market for verification systems for autonomous systems or AI systems. This is a wonderful business opportunity right now. I think at the moment I would invest in 10 times more autonomy verification companies and 1/10 as many cybersecurity companies in terms of the importance to the economics at the moment. And that is the end of my quick pitch for the importance of AI safety right now. Thank you.